Hey guys, today we took a look at thermal expansion, which is the expansion of materials when they're exposed to heat. So when they're exposed to heat, they expand, but when they are cooled, then they contract. Now, water is a special material in that it is most dense at 4 degrees Celsius. And below that, from like 3 degrees down to 0 degrees, as it freezes, it becomes less dense and it rises to the surface of a lake. That's important for fish to survive in the winter because they settle at the bottom where the water is about 4 degrees. That's the densest. That's why ice floats. The thermal expansion equation is the change in the length of the substance is equal to its coefficient, which is alpha, and that's a specific number for each material, times its initial length times the change in temperature, and that's going to be in either Kelvin or in Celsius because those are the same size units. So the unit for alpha is K-1 or 1 over K. This chart shows a few substances and their coefficient of thermal expansion. These are all to the power of -6, 1 over K. We'll take a look at, we'll probably use lead, copper in just a moment. This first example is on the Eiffel Tower. It's made of iron. So the tower is 301 meters high. That's going to be the initial length. And that is when the temperature is 22 Celsius. Remember that the change in temperature is the final temperature minus the initial temperature. And the question asks, how much does the height decrease when the temperature cools to 0 Celsius? So we are looking for this change in length. The final temperature is 0, the initial temperature is 22. And we get this coefficient, alpha, for iron from the previous table. 12 times 10 to the -6 power. So the change in length is 0.079 meters or 7.9 centimeters shorter. If you have the initial length in meters, then the change in length will be in meters. If you have the initial length in centimeters, the change in length will also be in centimeters. So any unit, meters, centimeters, or millimeters is fine to use in here. You won't have to convert because one is equal to the other. It's just that this one is related to the coefficient times the change in temperature. The second example is on expansion joints. So these are the gaps in the bridges. You may have driven over a bridge and felt a bump or a couple bumps, and those are the expansion joints, and they're little gaps, and that is there on purpose so that when the bridge shrinks in the winter, it can close the gap, and when it expands in the summer, it can widen that gap. If those gaps were not there, then the bridge would just collapse or crumble on itself because it doesn't have space to expand or contract. So in this problem, a lead slab, PB is for lead, is 88 centimeters. And it is near a copper slab. Cu is the abbreviation for copper. I'm going to put a wall here. And that copper slab is 76.5 centimeters long. When both slabs are at an initial temperature of 0 Celsius, the rods are placed in line with a gap of 0.7 centimeters between them. And the distance between the far ends is 165.5. This is important because this is going to cause the two metals to expand together and close that gap. So this is 165.5 centimeters. Now I'm just going to go ahead and convert these to meters because that is an SI unit for length. There we go. And for this problem, we're going to set up a system of equations where the linear expansion of this one is going to be equivalent to the linear expansion of this one to close this gap, where these two substances and their expansion rate are connected through their final temperature. So we have the change in length of lead equals the coefficient of lead times the initial length of lead, which is 0.88 meters, times T final minus T initial, which is 0 Celsius. So they start at the freezing point of water, and then they're going to be heated to expand to fill that gap. This is important in like mechanics and such. I'm building bridges, obviously, here. The other equation is going to be the change in length of copper, which is equal to the coefficient of copper times its initial length, 0.765 meters, times the final temp minus 0 degrees Celsius. Okay, now since these two are connected through the final temperature, that means that that is going to be the same for both of these. We're going to set these two equations equal to each other and then develop just one unknown variable that we can solve for. So in order to isolate TF, we need to take the coefficient, which is given here, times 0.88 and divide it out on both sides. So we get delta LPB divided by the coefficient of PB and 0.88, that equals to the final temp. We're going to repeat for the other equation. Again, divide by 0.765 and alpha. The change in length of copper is divided by the coefficient of copper, and 0.765 equals the final temp. Now we can eliminate that middle variable there and just set these two equations equal to each other. But the problem is we have two unknown variables. The change in length of lead is not going to be the same as the change in length of copper, as the rate of that change, because lead expands at 29 times 10 to the negative 6 units per Kelvin. Degree Kelvin, if you will, but it's just called Kelvin. Whereas copper expands slower, only 17 e negative 6 per Kelvin. Okay, so the closing the gap is not going to be equal. This one's going to move farther than this one. But what we can say is that this gap, which is equal to 0.007 meters, is equal to the sum of both of these expanded. So if I want to solve for just PB, I'm going to take this 0.007 minus the expansion of copper to solve for just the expansion of lead. So again, instead of the length of copper, we're going to replace that with 0.007 meters minus the expanded length of the lead that gets in the way of that gap. So that should make sense. This is the gap. The gap is equal to the change in length of lead plus the change in length of copper. So we can rearrange that to substitute for the length of copper. So we're just going to carry down the rest of this and solve for delta LPB. In order to do that, we need to do some algebra. First, we're going to multiply these two, and then we'll multiply these two. Those coefficients are found here or in that table. This one's for lead, and then copper is here. So when we multiply those, we get this denominator is equal to 2.55 e negative 5 meters per Kelvin. All right, this is in meters times 1 over K, so you get meters over K. These two multiplied together give us this number. So we're going to continue the algebra to solve for the unknown variable. We need to combine them. So we're going to multiply this denominator on both sides. So it cancels out on this side. And over here, we get that one on the numerator divided by the denominator times delta LPB equals the numerator of this equation here. Next, I'm going to resolve this fraction. So when you divide these two numbers, notice the times 10 to the negative 5 is going to cancel out. So it's like 1.3 divided by 2.55. You get about a half. Keep your digits in your calculator until the end of the problem, then round to significant figures, where you might be off by a little bit in your answer. Okay, so now we have 0.007 minus delta LPB. In order to combine these terms, I'm going to add delta LPB over here to this delta LPB. So we're just going to add one unit of it, plus 1, you get 1.5096 times the change in length equals 0.007. That's all that's left. Lastly, you want to isolate your variable. So take this number and divide it on both sides. And you get the change in length of lead equals 0.00 0.464 meters, or about 5 millimeters. So that is the smallest unit on the ruler. So that's a centimeter. So these little marks, 5 of those, that's 5 millimeters right here, which is actually pretty significant if you're trying to get metals to fit together. But we're not done yet. We have to take that number and we have to find out at what temperature does the contact between these two joints occur. So we're going to take your number and substitute it back in to this equation here for the change in length of lead to find that final temperature. And alpha lead is here. That's 1 over K. And TF minus 0 is just TF. Okay, so now we're going to divide by this on both sides, and we get our final answer. Which is about 182 degrees Celsius. So it has to go from 0 all the way up to 182 degrees Celsius for that contact to occur.